All right, welcome back. So I've decided to have a series of what I'm going to call mini lectures, which only requires me to record my writing rather than also myself. But these are also going to be inspired by student comments. So a student wrote to me just now and asked if we could perhaps have a mini lecture on how to get the wave equation out of a physical system. And we did some of this in class, but that was a long time ago. So I figured, heck, what a great idea to start a little mini lecture series. So the first thing that I want to remind us of is just a little bit of math that we're going to use later on in a substitution. And at the beginning of this is something that you learned in Calc 1, which is the definition of a derivative. And so if I just think about a derivative the way you probably first learned it, we define, I should have a define symbol here, we defined a derivative to be the limit as h goes to 0 of f of x plus h minus f of x over h. And how we visualize that is we think about taking our point, f of x, right, which, let me put it right here, right in the middle of this function. And then I take some point to the right of it at x plus h, and I draw the tangent line there, and then I let this point go to here, and I watch how the slope of that tangent line changes. And as the limit as h goes to 0, the slope of the tangent line is the slope of the function at that point. But that's really just one way of defining a derivative, right? And actually, depending on who you had for calculus, you might have learned this as the right-handed derivative because I'm comparing my function at x to a function to the right, to a point to the right of x. But equivalently, I could define the derivative in the left-handed way, right? There's no reason to only assume that the whole world is right-handed, right? I could, instead of comparing f of x plus h and f of x, I could compare f of x to f of x minus h. And pictorially, what that means is that I start over here, right? And I draw tangent lines at x minus h, and then I take the limit again as h goes to 0. And for a well-behaved function, those two things should be equal to each other. There are obviously examples of functions where those two things are not equal to each other, discontinuous functions, for example. But these are two good ways of defining derivatives. And since they're both good ways of defining derivatives, I'm going to take the two and I'm going to take their average, right? Which means that I'm going to add them together and then I'm going to divide by 2. So if I look at this, I get that I have f of x plus h. Right, so let me write it down. df dx is equal to f of x plus h minus f of x plus f of x minus f of x minus h, all divided by, well, I have to divide by 2, right, because I'm taking the average, 2h. And I should leave a little bit of room for my limit as h goes to 0. Right? And now what's fun is that the f of x's actually cancel here, right? And that's kind of cool because in this definition of the derivative, where I'm sort of going at it from both sides, I don't actually need to know the value of the function at the point that I'm trying to study, right? I'm comparing a point to the right to a point to the left. Now, of course, as h goes to 0, it's clear why that ends up being the derivative of the function at f of x. So if I take that as my definition of a derivative, I can go ahead and build a second derivative, right? Now, so the second derivative of x is going to be the derivative of the first derivative of x, which means that, I'm going to do it from both sides, right? So df dx at x plus h minus df dx at x minus h divided by 2h. I plug in what I had from the previous page, and now this extra minus sign makes it so that my midterms don't cancel anymore, but I get the limit as h goes to 0 of f of x plus 2h minus 2 times f of x plus f of x minus 2h, okay, all divided by 4h. And now this is neat because now the point to the right and to the left both have positive signs, right? So, and the point that I'm looking at has a negative sign, and it sort of starts to feel like I'm calculating something like curvature, which is, of course, exactly what the second derivative is. But in order to make this a little bit simpler, since I'm never evaluating anything at h anymore. I'm only evaluating it at 2h or minus 2h. it's actually a little bit better rather than taking rather than looking at plus 2h and minus 2h and 4h to go to the place where 2h goes to just h, right? And then I'm left with a much better definition of the derivative, the second derivative. Df dx squared is the limit as h goes to 0 of f of x plus h minus 2f of x plus f of x plus f of x minus h divided by h squared. I can't believe I forgot my squareds here. When I plug in that second derivative, I end up with squareds, and of course that's why 2h going to h. That's why 2h going to h makes sense. Let me move this so that I'm not tempted to forget where it went. Okay, and this is the thing now that I'm going to use as my definition for the second derivative. Okay, and it's perfectly legit as a definition for a second derivative, and it makes total sense in terms of all of the calculus that you've ever learned. Okay, now back to physics. Okay, the question was, how do we get the wave equation out of some of these physical systems that we're seeing? So let me look at the beads on a string problem. So this is the one that we introduced in the textbook. The math is identical to the math that we had for the n blocks with n plus 1 springs. You end up with the same coefficients, that same pattern, when you try to do the normal modes of the two different systems. And of course, that's because both of those systems inevitably end up being described by the wave equation. But here I'm going to look at the beads on a string. So I have some number of beads. It doesn't really matter, but they're spaced apart by delta L. And I'm going to start by just studying one of them, y sub n, and the one to the right is y sub n plus 1, and the one to the left is y sub n minus 1. So if I zoom in on this y sub n, I want to find out what are the forces that are going to be acting on this bead, what is going to make it move, or what is going to make it accelerate. And there are really two different forces, right? There's a tension from the right and a tension from the left. I want to start by just studying one of them because I think going through this slowly is actually really important, okay? So the tension is pulling upward to the right. Now, for small displacements, we can make some argument that the distance between them along the string, which we know is going to be delta L, is going to be much bigger than the difference in their height, right? So this is, again, we're near equilibrium physics, and so we're not going to bend this too much. If you think about it like, some violin string or something like that, it doesn't move. It doesn't move in the transverse direction much compared to how long it is. So delta L is going to be bigger than this height difference. Well, what is this height difference? Well, it's y sub n plus 1 minus y sub n, right? It's how high is the n plus 1th bead compared to the nth bead. And so when I look at the tension, right, when I look at this tension force, and I try to find out what is the component of the tension that's going to cause it to move up and down, well, let me throw a theta on here, right? So this is going to be T sine theta, right? Okay, well, let me move this over. T sine theta, well, sine theta is, let's see, so it's the opposite over the hypotenuse. Well, in the small angle, let me write that out. So this is T times the opposite, which is y sub n plus 1 minus y sub n, divided by the hypotenuse. Well, okay, we're going to, small angle approximation, the hypotenuse is approximately equal to delta L. Okay, now it's really the square root of delta L squared plus y sub n minus 1. But that thing is small compared to delta L. So another way of saying that is that sine theta is approximately equal to tan theta. And if I finish my ka toa, opposite over adjacent works for tangent. Okay. So the vertical component of the force on y sub n due to y sub n plus 1 is approximately given by T times y sub n plus 1 minus y sub n over delta L. And that's something that's going to stick with us now as I move to the next part of the problem, which is to add up all of the forces acting on y sub n. And since there are two forces acting on y sub n, there's going to be that contribution from the first force that we saw, right? T times y sub n plus 1 minus y sub n divided by delta L. But then there's also a force given to us by the bead on the left, right? And that one is going to have exactly the same form because the tension is the same. But it's going to be y sub n minus 1 minus y sub n over delta L, right? If y sub n minus 1 is above y sub n, then it's going to move it up. And if y sub n minus 1 is below y sub n, then it's going to move it down, right? And now you start to see the magic happen, right? So this is there's a tension in both, so I can pull that out. And I'm going to write this as y sub n plus 1 minus 2 y sub n plus y sub n minus 1 divided by delta L. Okay, and now this should already start to remind you of two things. First, it should start to remind you of every matrix element that we did when we were talking about the finite system of blocks, right? It always had that pattern, 1 minus 2, 1, right? And here, when I write it like this with the delta L, and I know that I'm going to be moving towards the continuum limit, and I know that delta L is going to start to go to 0, everything starts looking like second derivatives again, right? And that's the magic that's about to happen. So as I go to the continuum, three different things are going to happen. First, the mass of the bead is going to approach some continuum limit where the mass of every little section is given by how big is the section times the mass per unit length. And that's given by this mu. So this is per unit length. At the same time, where is the nth block is going to be replaced with a function that tells me where is every point on the string. And therefore, all of my other blocks, like f of n plus 1, is going to be given by f of x plus delta L, right? It's going to I'm going to replace all of my individual piece of information, f sub n, with a complete function, which we're going to call f. And of course, all of this happens in the limit as delta L goes to 0. So if I now plug this into, and I just recopied my definition of the second derivative from before, but I'm gonna rewrite my wave equation now. So I'm gonna rewrite my equations of motion. So I had m y sub n double dot is equal to t times y sub n plus 1 minus 2y sub n plus y sub n minus 1 over delta L. So let me first replace m with mu times delta L, and then I'm gonna change all of these things to I'm gonna change them all to f's. Okay, and so let me do a little bit of rewriting. So I have now the second derivative of f of x, right? That's this thing. My delta L, I'm going to pull it to the other side. I'm also going to pull my mu to the other side, so I have a t over mu times the limit, right? In the continuum, I'm going to let delta L go to 0 of I changed the y's to f's, f of x plus delta L minus 2 f of x plus f of x minus delta L divided by delta L squared. Okay, and now, of course, that's just this, right? That's just what I had for the second derivative with respect to space. Even the limits work out, and unlike when I was working at the board, I'm 100% confident that all of the h's and everything are in the right place. Okay, so what I'm left with then is that, and I'm going to put it in red just so that this is a big day. F double dot is equal to t over mu times df dx squared, right? That the second derivative with respect to time, which came from Newton's laws, is now related to the second derivative with respect to space, which comes from looking at the forces. And that's the wave equation, right? And I can rewrite it now where mu over t gives me the wave speed. This is something that you learned in modern physics, but I get out the wave equation from that simple system. And of course, the assumptions were that I was in near equilibrium physics, right? And that's the thing that keeps coming back to us as the most important part of getting these great results, is that the genericness of something like the wave equation comes from the fact that all along I could trust that I was doing something sort of to first order in the Taylor expansion, right? And so the left-hand side came from, only worrying about the first order in time, like I did with the shoe. And then the right-hand side, right, had this built in, well, the beads aren't moving up and down as much as they are separated, right? And so I was still in some near equilibrium description when I got to the wave equation. And that's all you end up with, right? Second derivative with respect to space, proportional to the second derivative with respect to time. And that's that.